Okay, my name's Tom Tecco with XLDyn. We're going to talk about product design using our software XLDyn together with Altair Activate. Also have with me on the line Phil O, our Chief Technical Officer, who will be available during the question and answer period. Okay, so a little bit about the strategy or thought behind the software and the company. Our goal really is to provide a flexible, easy to use tool for product development activities, but following a model-based systems engineering methodology. And we wanted something that was fully integrated and intuitive and more easy to use. Currently, a lot of companies in the process of implementing model-based systems engineering find it difficult and costly integrating a lot of different software pieces to try to accomplish their goal. Just looking at the overall product development process, many times projects, obviously they start out with customer expectations. You may have some documentation of what you want the new feature or function to be. You might even have written down or created some requirements and what you think parts you need, diagrams, pictures, simulation models may be, you may have some simulation models. Many times these artifacts that I just mentioned, evolved from previous design, so there's an opportunity for reusing, some of the design artifacts. But the objective then is to really come up with a quantifiable set of requirements that well-define what the functionality, capability of the product needs to be. You need to determine what parts, whether they be physical or logical, instantiates the design and provides the functionality. You need to validate and verify the requirements, and also before you finalize your decision, you really want to look at different design alternatives so that you make sure you got the best combination of parameters and characteristics for the product that you can come up with. Okay, so how can MBSE help? Well, hopefully that you'll be able to provide a balanced design that reflects the voice of the customer. And as I said, you want the MBSE methodology to be able to help you consider all different aspects of the design, organize all the deliverables, make sure you have the documentation that goes along with the decision-making process. The design deliverables are typically bill of material. Could be software, could be hardware, could be control systems, whatever. Set of requirements that are satisfied by the functionality that they have, and any supporting documentation that came up from the validation and test result process. You want to be able to provide also during the development process with MBSE status reports on the project that you can share with team members in a collaborative manner, and also with third parties as necessary, suppliers and other design partners. So what is XLDyn relative to what we just talked about? Well, we consider XLDyn to be a product development tool that follows a systems engineering methodology as opposed to a SysML diagramming tool. Okay, it's composed of a few components. One of the main modules is XLSE for authoring SysML compliant diagrams. It has a user interface that guides the user through the data input process, and then renders the diagrams very quickly and effortlessly. And one of the key aspects of XLSE is it has many other design analysis and simulation tools integrated into XLSE, besides the SysML authoring tools. Everything is stored on what we call the SE server, so all the artifacts are on there for the model. And last of all, XLDyn includes a 1D multiphysics simulation tool. But in the example today, we're going to be looking at the Altair Activate product, which we have integrated with our software. So let's take a look at how the collaboration part works. You know, if you take a look on the right, this diagram kind of represents what we call the SE server. It's composed of a few different things. You have your main projects that you can create, and these projects contain all the digitized artifacts, requirements, parts, diagrams, use cases, state machines, schematics, simulation models. These main projects can be created from the library. They can be created. Main projects can be created from other projects, or the artifacts can be created directly in the user interface. So you can have a combination of things available. From the main project, you can create sub-projects. So basically, you can assign portions of the projects to different individuals. I'm going to show you a little bit more about that later. And then, or conversely, you can also create variants. So if you want to do a study to compare different design alternatives, this is a great way to do that. And I don't think I mentioned that you can import and export data to and from other enterprise data stores as necessary. Little green check marks means we're going to go into a little bit more detail on that later. There's a lot of design and analysis tools capable within XLDyn. So as I said, part of the process is you can create and manage requirements and parts. You can create use cases and multi-level use cases that can be linked. You can develop activity diagrams. I'm going to talk about them a little bit more in a minute, but basically this is an example of our activity diagrams. The unique thing about it is that it's actionable. You can actually perform calculations from the activity diagram, as well as the state machine diagrams are actionable. You can create domain maps and perform FMEA analysis. As I said, we had the 1D simulation. Another thing that I'm going to spend a little more time on towards the end is you can do system level design of experiments, including with test data. And I'm going to show a few slides towards the end that gives an example of how to apply that. You can make schematic diagrams and the internal block diagrams. From the program and project reporting status standpoint, you can look at requirements. You can look at cost, weight against targets at any time in the development stage and create reports on that. You can, as a program leader, you can take a look at the percent of the requirements that have been satisfied and completed. And another thing that we're going to look at in a little more detail is some of the capability around, comparing design variants. Okay. One of the key aspects of model-based systems engineering is verifying requirements and having those verifications associated with the requirement. And so we have the capability of basically verifying almost any requirement. And I'm going to talk about that in a little bit more detail. But as I mentioned before, you can verify requirements with our parametric diagrams, activity, and state machine diagrams because they are actionable. You can run the simulations directly from the diagram. So as you can see in this case, I've got on the right here, I've got a requirement for a cooling system, and I've got a state machine, state diagram connected to it. I can put those parameters in the cells, and I can actually perform the simulation directly from the diagram. Okay. So the verifiers include XL1D models, and as we said, state machines and activities. You can also have cell equations and other Excel workbooks as verifiers, as well as third-party simulation models which are integrated, such as Altair Activate, and we're going to take a look at that in a little bit more detail. So, but these are called internal verifiers, and that's because they can be, the simulations can be run directly from the diagram view. We also have external verifiers, in this case over here is an example. The external verifiers can be for test results or for non-integrated simulations. So if you have maybe some large scale simulation that you're doing and you want to use the results of verifier model, verifier requirement, you can use an external verifier. And then you can connect other design artifacts to the requirements. So if you got videos or Excel workbooks or JPEG files or whatever, you can associate them, any file with a requirement, and then open that file directly from the diagram view. So you got everything in one workbook. So let's take a little bit more closer look at the detailed results. These are the four we're going to look at: project construction, Activate as a verifier, system level DOE, and variant analysis. So to construct a project is very straightforward, particularly when you have reuse of previous components and models. You can quickly form a project team by the team members that have been entered in, or the users that have been entered into the system. From a drag and drop perspective, you can create a team structure, and then you can create a project. I'm not showing that on here, but here's a project that's been created. But the project can have a lot of details with a lot of requirements already potentially defined, or it could just have categories. You can develop your own hierarchy for the project. You can bring in existing parts that you want to use. And then you can, from that hierarchy that you can set up, you can assign portions of the projects to the individual team members just by a drag and drop process. Then after that, you can assign part ownership to the team members. And then later on in the process, if the team members want to add more content to the project, they basically have three alternatives. They can go to the library, which is public to all of the users in the system, and they can bring content over from the library and into the project, or they can bring it from other projects, or they can enter or add requirements and parts and diagrams directly into the model. So those are the three ways that you have to add content. Once you have, at any point in time, you can draw the current status of the model construct just by pushing a button, and you get the complete model drawn with the hierarchical relationships and all the diagrams. And for the verifiers, the parameters that you've chosen get put into cells along with the MOEs. So very easy to get going with the project. So let's take a look at Activate as a verifier. We have it integrated in XLDyn. So to use Activate as a verifier, in this case, this is a braking model for a vehicle. So I have a requirement stopping distance. I just right click on it and I say add change the verifier. It brings up a panel. From the drop-down menu, there's about 7 or 8 different possible selections for verification methods, including the external verifiers that I discussed, the state machines. In this case, I'm going to pick an activate model. Once I select that, then it will list all the models in the next panel that I have access to. I select the model that I want to use. It tells me what MOEs are available, measures of effectiveness, which we want to match up against the requirement. And it also tells me what design parameters are available. So I merely select the MOE that I'm going to use, and I select the associated design parameters. The next step is that the constraint block is drawn, or node is drawn, and the parameters I selected in the MOE are put into cells. And if I want to run this simulation directly from the diagram, I can adjust the parameters, the mass, the drag coefficient, the wheel radius, and so on. And then I just can calculate the simulation directly from the diagram. It'll put the result back here in the MOE box, the 57.8, and then it will update the value every place in the system. So in all of the status reports and summary tables, the results get updated automatically. Okay. Likewise, if I want to see what's in this model, I can select this constraint block. It knows it's a activate model, and then I can come over and launch activate, and it knows which model I want to look at, and it will open up activate window, and you'll get the model available for you to work with in the native activate. Okay. So how do you use these verifiers? Well, you can use the verifiers by doing a design analysis with say design of experiments. I'm not going to use activate verifier in this one, but we have done that, and you can do it. But in this particular XLDyn model, I basically have a vehicle, what I call a concept level, high level vehicle model. It has 13 different MOEs available in the model. We're going to study 2 of them. In the fuel economy area, I have an MOE that I'm going to select called City Highway Combined Fuel Economy. The design parameters are weight, coefficient of drag, and frontal area. And the other MOE is the time to accelerate to 60 miles an hour from 0. And the design parameters, again, are weight, coefficient of drag, and the frontal areas. So the process is quite simple. You select the MOE here, 0 to 60, and combine. You select the design parameters here that you want to study. You choose the level. You can put weighting parameters, weighting factors on the MOEs. Some are more important than the other. You select the level of the DOE that you want to run, and then it will tell you the number of runs you need to make. In this case, it was 8. So it runs 8 simulations of the 0 to 60 acceleration and 8 simulations for the fuel economy by adjusting the parameters. Okay. Results get printed out of the table for you. Now, just bear in mind here, in this particular case, we estimated vehicle mass using an equation or a model that uses powertrain mass and track width as a way to estimate the overall vehicle mass. So there's different mass models for different classes of vehicles that have been developed. But in any case, mass gets substituted with powertrain mass and track width as a parameter. So you can see the results here. These are my design parameters: engine transmission mass, track width, frontal area, and CD. These are the MOE results from the 8 runs for this combined city highway and the 0 to 60. These are the target values and the requirement. And you can see from the result that the best combination of parameters was run 5, as it had the smallest total deviation. And in addition to that, we calculate the main effect. So which one of these 4 parameters has the largest influence on the design? And it happens to be the track width of the vehicle, because this model has that parameter as being the largest influencer of the vehicle mass. Okay, so other ways to compare these designs would be taking a look at the variant analysis, which we have available, and you can analyze any number of projects. You can just select the projects that you want to compare, and it'll construct a table for you that will show the different variants on the left side, all the different MOEs that are available in those models. And at the same time, it will, you can do them 2 at a time by the drop down up here, selecting the models you want to compare the bills of material for. So there's a parts list, whether it be logical or physical, or associated with each one. And in this case, I'm comparing an internal combustion engine to an electrical vehicle. And so obviously the difference in the part list is the electric drive components, and over here the components associated with the internal combustion engine. So this allows you to compare the performance of the variants and the composition of the variants. Okay. Additionally, we've used a lot of different simulation models, whether they be cell equations or other macros or worksheets or activate models or whatever. And those models have different parameter settings. Those same models may be used in 2 or 3 different variants. The only difference is that the parameters are set different. So I can take a look at, instead of comparing BOM parts down here side by side, I can compare the parameters, and I can see that between the internal combustion engine and the electric vehicle, one of them in the fuel economy model had the frontal area set at 1.8 meters, and over here it was 1.95 square meters. So you can compare the parameter settings to see where they were between the 2 models. And if you want to look at the detailed mass and cost for each model, you can do that too, broken down to the individual part level. Okay, so that's kind of a high-level overview and some application of XLDyn. XLDyn really supports product development teams with an easy-to-implement and collaborative environment, while adhering to a model-based systems engineering methodology, trying to bring together all the different tools that are needed in the product development process. We have tried to integrate an extensive set of decision-making tools for the engineer. So basically, the idea behind XLDyn is to provide a tool set for engineers to develop designs, and then the documentation becomes a byproduct of the process, as opposed to the approach of some systems engineering tools where the tools focus more on documenting decisions that have already been made. So that concludes my presentation, and I guess we can open it up to questions.